Okay, the first step is to draw a picture. And in this case, this would be like our real circuit, and then this is our very simple circuit diagram. So the first thing to notice is that we have a loop. Again, I recommend starting at the positive terminal of our battery, and so this is our loop, right? The other thing to notice is that we can define what direction our current is going, which again, we say that our current is going to flow from the positive terminal of our battery. So this is the way current is going. Now, I would encourage you to actually continue that through the entire circuit so that you actually can see which way it's going through the resistor. So that's really the starting point. Now we can do the full analysis, and the goal would be to understand how the potential difference across this resistor is relating to the current and relating to the EMF of the battery. Before we do the calculation, it's important to understand a few of the simplifications we're making. One is that we have ideal wires. The point of that is that effectively the resistance of the wires are zero, such that delta V here equals zero. That's not to say that the absolute potential is zero, but simply that if you have 9 volts here, that you also have 9 volts there. So we don't actually care about the length of the wire. Now be careful, because there are going to be some scenarios where you don't want to use ideal wires, where you do care about the resistance of them. But anytime you have resistors in the circuit like this, you typically want to use the ideal wire. The second big approximation that we almost always get to make is the ideal battery. And the idea here is that our delta V across the battery is simply equal to the EMF. A non-ideal battery has a little resistor in series, so rarely do we need to worry about that. Finally, here we're saying that it's an ohmic resistor. Now, this is like the opposite of a paradox or a contradiction. This is kind of a tautology, in that resistors by definition are always ohmic. However, what you've seen is that sometimes we encounter problems where we think about other materials. So for instance, maybe we have a person and we're going to think about the path from one hand to the other. Now, their arms are not literally a resistor, but we're going to approximate it as ohmic. So note that you can theoretically draw circuit diagrams where we're simplifying things to be resistors. Another example is the heating element in a toaster, or maybe the heating element on an electric stove. So these are things that act kind of like resistors, and we're going to simplify it by modeling it as a resistor. So those are things that go into our recipe for actually doing this calculation. So as I've already said, you want to start by picking your loop direction or your current direction. Again, in this case, we only have one loop, so the loop and our travel direction will be the same. So then we want to determine each delta V, and we see that for the battery, because we are traveling from negative to positive, that we have positive E. Again, curly E is our EMF of the battery. But then on the resistor, our current is going through the resistor this way, and so we have a decrease, right? Note that minus sign. So when we then set up that the sum of delta V equals 0, what we simply have is that V battery is plus E, and then we have minus IR equals 0. What this perhaps unsurprisingly tells us is that the EMF of our battery divided by the resistance gives us the current. So this might just look like Ohm's law to you, and it's really kind of a variation on Ohm's law, but it tells you that the current coming out of the battery depends on the EMF of the battery and the resistance, or the load, we frequently call this the load, of the circuit. So again, here we haven't gotten anything too special, but this will become more interesting and more complicated as we add more than 2 components to our circuit. I'm going to talk you through kind of a strange example. So let's start just by focusing on what's on the left. We have a circuit diagram, and note that there's actually 2 batteries in it. So we have a 6-volt battery on the left and a 9-volt battery on the right. And notice how they're actually oriented. So we can start by assuming, as I frequently do, that the current is going this way. And again, you want to make sure that it's going the same way around the entire loop. Well, so in this case, we want to, as always, say that our total sum of delta V is equal to 0? Well, here we are going to have our a gain of 6 volts. And so we start with 6 volts. And then we come over here and we say that, oh, okay, here now I'm going to have a decrease of I times R1, which is 4 ohms, but I'm going to leave that as a variable. Now why? Because I've assumed that my current is going that way. Now I get to this. Note that I'm going from positive to negative, so I have minus 9 volts. I get to this resistor, and I'm going to have minus whatever my current is. I don't know the current. I times R2, and that must equal 0. Well, now there's something kind of strange here. Let's combine all of my battery potential on the left. So if I have 6 volts minus 9 volts, that gives me minus 3 volts. And on the right, I'm going to move over IR1, IR2. I have I times R1 plus R2. Notice now that I have a minus sign on the left and current on the right. This means that I've chosen the wrong direction for current. Actually, current must be going the other way, right? So effectively, I'm getting that I equals negative 3 volts over R1 plus R2. So this is a case we've picked the wrong direction, you get a negative current, that's fine. So now let's actually do our analysis with the correct direction and work with this plot. So we're going to go in the same loop direction, but we're going to go the opposite direction with current. So I've tried to label this really explicitly, that green on the outside is the loop direction you're going, red, the current on the inside, is actually going the opposite way. So we're going to start here. So that's my start point. And we're going to assume that I am starting at 0 volts. And as a preview, something that you're going to see in a future video is that we can do this through grounding that point, which doesn't change anything about our circuit. It just allows us to define that as 0 volts. So here we go. We're at 0 volts on the plot. Now we go through my battery and I gain 6 volts. So that takes me up to this point. So this region here is being in the battery, where this is our 6-volt battery. So then we are actually in this flat region where that's just being in the wire. That doesn't really matter. But now we get to this resistor. Note that I am traveling this way through the resistor, but my current is going this way. So this is a rare case where you actually gain potential in your resistor because you are actually going opposite of the current. So we then have this increase in 2 volts, and the reason why it says 2 volts is that this is actually calculated the current already numerically and is plugging that in where I haven't explicitly shown that. So this is being in R1. You go up because you're going opposite direction of current. This is a fairly confusing example. I figured I would show you a hard one rather than an easy one. We then get to this battery. Note that we are going from positive to negative, which means we're going down 9 volts. So we go from 8 volts down 9 volts because it was 1 amp of current. So we're now at negative 1 volt. That's okay. That's totally fine. We then come through. Again, the wire doesn't matter. So this here was our 9-volt battery. And then we get to this last resistor. I am still going opposite direction of the current, which means that every resistor still is an increase. And so I go from -1 up to 0. That brings me back to my start point, which is now also my finish point. So note that here I'm back at 0, which is good, which needs to happen since I've returned to my initial point. So this is a confusing situation because your initial loop direction is actually opposite of your current. And so plotting that is a little awkward if you don't know that you're actually going opposite of your current. Your plot wouldn't work out. So make sure that you think about this and calculate your current first, and then you could have actually just gone the opposite direction in your loop to do the analysis. It still would have worked out.